Okay, so here we go. Information you need to know about the midterm exam. Here's when and where. What you need to bring: calculator, pencil, brain. Implied in the brain is that you will have given yourself adequate sleep. Make sure that you get sleep the night before. So we will feel that, oh, I can stay up till 2 o'clock and I'm still sharp. Science says you're wrong. Still finish papers. It's just that when you go back and you read them, you think,
what was I writing?
Exactly.
yeah.
Oh, so when do you advise me to go to sleep on Tuesday?
Well, I don't know how much sleep you need per night. But if it were me, I would need 8 hours to be really sharp. So you could work backwards and do the math. You're a teenager, so technically you need more like 9 or 10. Right. Doesn't work for you. You think it works, but it doesn't work. Nice.
Weekend 10 or 12.
Not sure what that's all about.
Sometimes. It depends on Friday.
Let's see. What do we have here? Anything else? Yes.
Those 4 to 5 hours.
These are optional in the sense that I will not collect them. However, comma, only a fool would not do that.
How do you put this one? They are full, they don't do it.
Yeah, it's not cool at all. Right, the point is that at some point we move from scare quotes into reality. You caught the point. Okay. And with all that said, let's jump right into it. What do you need to know? Well, let's talk about pre-calc stuff that you guys have mostly picked up at this point, but I just want to emphasize. First skill, you need to be able to mark up a unit circle. So that you can evaluate the trig functions at the special angles. So that, in particular, you need to be able to do things like solve sine x equals 1/2 on 0 to 2 pi. Those kinds of things. And you also need to be able to evaluate things like the cosine of 3 pi over 4, stuff like that. The preferred method for marking up the unit circle, in case you're rusty on that, is to start at the 4 corners and mark your angles going around, like so. And then you mark your coordinates. And then you go through and you fill in your multiples of pi over 6, and you fill in your multiples of pi over 4 as you walk around and give the coordinates for each of those. I'll do just the first quadrant right here. So this guy would be pi over 6, pi over 4, and pi over 3. And the coordinates are going to be root 3 over 2, comma 1/2, 1 over root 2, 1 over root 2, and 1/2, comma root 3 over 2. Evan and or Lindsay did a really nice blank template for that you can use to practice with. And I think I put it on Edward, didn't I? I'll make sure that it's...
I think it was Catherine. She was really hot on my
Thank you.
iPad.
Yep. Good job. So if you are at all fuzzy on that skill, make sure you practice. The second thing that we did that you want to make sure that you can do are exponentials and logs. And in particular, you need to know your exponential properties. E to the x times e to the y can be simplified as e to the x plus y. And e to the x over e to the y. And e to the x to the y. E to the xy. And the corresponding log properties. The log of a product is the sum of logs. The log of a quotient is the difference of logs. And the log of a power is power times the log. Highly recommended that you commit those forms to memory so that you can actually use them to solve problems. We also looked at the graphs of exponentials. And in particular, my general exponential graph is going to look like this. As long as my base is bigger than 1. Or it is going to look like this if my base is between 0 and 1. We don't do bases that are less than or equal to 0. A base equal to 0 would be a boring graph. And a base less than 0 would give me strange, complex, or imaginary numbers. There are special points on the graph. This graph goes through 0, 1, or if I have the more general exponential, y equals a b to the x, then y of 0 is going to be equal to a. This corresponds to an initial value or a y-intercept on the graph. And I also have an asymptote that is the same in every case, y equals 0. So that in general, the limit as x goes to negative infinity of b to the x is equal to 0 for b's bigger than 1. Understand why this is true. If b is larger than 1, then as I raise b to greater and greater negative powers, what does a negative exponent mean? Reciprocal, right? Then I'm taking 1 over b to the x to a larger and larger power. That's going to go to 0. Because I'm dividing 1 by a very large number. Since this is the exponential, the graph of the log is its inverse. Instead of going through the point 0, 1, it will go through the point 1, 0. Instead of having a horizontal asymptote y equals 0, it will have the vertical asymptote x equals 0. And the graph will look just like this. Are there questions about any of this? Awesome. Great. Well, all of this goes on Edline, so I'm going to zip through, and then if you want to pause it and go back. When we talked about limits, let's get some definitions down. The limit as x goes to c of f of x equals L is a special statement that means something specific. F of x is arbitrarily close to L. When x is close to, but not equal to, c. Just like so. Close, yeah, for numerical purposes, the close that we will take is 0.0001 out to the fourth place.
Okay.
Yep.
Are we going to have definitions?
You might very well. Yep. And the reason I say that is that this strict legal language is the logical form that guides you. So even if we didn't explicitly have definitions, like if I didn't ask you, give me the definition of limit, I will still ask questions to see whether or not you know this strict legal language. We had to modify our statement a little bit when we consider the limit as x goes to infinity, if the limit as x goes to infinity of f of x equals L, then this means that f of x is arbitrarily close to L. For large enough x. For large enough x. And likewise, the limit as x goes to negative infinity of f of x equals L means f of x is arbitrarily close to L for negative enough x. Or in other words, x's negative numbers with a large size. And finally, we also had infinite limits. The limit as x goes to c of f of x equals positive infinity means that f of x is large, f of x gets big without bound, or unbounded, for x close to but not equal to c. So these three definitions are ones that you should know and be able to apply, and the main place that we apply them is in reading graphs. So let's take a look at a graph and see what we can see about this graph. How about we actually put up a real graph? So here's graph, and we'll have a function here, and like so, and like so. And let's do that, so the graph goes like that. Okay, so we have all sorts of niftiness, nicenesses on our graph here. And so let's start asking and answering some questions. First question, what is the limit as x goes to 1, 2, 3, 4, 5 of f of x? Is that limit 4, 7, or something else? Why? Apply the definition. Your only acceptable answer is in terms of the definition. Yeah? Why?
Because it's for x close but not equal to c.
For x close to but not equal to 5, in this particular case, f of x is close to what value? Take a look at x is close to 5. And what do you see about the y values? What are they close to? They're close to 4. That's right. This limit is 4. Now, on the other hand, what is the value of f of 5? 7. Because when x is actually equal to 5, f of x is equal to 7. Does everybody see the distinction? Okay. All right. How about as x approaches 1 from the left? What is that limit?
4.
Definitely 4. Because for x's that are close to but less than 1, f of x values are close to 4 here. How about as x approaches 1 from the right?
When?
I don't know where you're talking about now.
You wrote like how I am.
Oh, lim. It's just me and mine. Then that limit is what?
1.
1, yeah. Yeah, just 1. Yep. And how about the limit as x approaches 1 of f of x?
Does not exist.
Does not exist. Why? because limits from left and right have different values. So we have to say that this limit does not exist. Good. How about the limit as x goes to negative infinity of f of x?
Negative one.
Yeah, how do you know?
Because it tells how it starts.
We have a horizontal asymptote on the graph, and the horizontal asymptotes correspond to the limits at infinity. And how about the limit? I'll put it over here. How about the limit as x approaches 9 from the left of f of x? Is positive infinity, right. And you want to include that positive sign right there to show direction. And the reason I know that is that f of x has a vertical asymptote, and the vertical asymptotes correspond to infinite limits. Great question. How do you find the horizontal asymptotes? The horizontal asymptotes correspond to the limits at infinity. So from a graph, we visually see the horizontal asymptote, and then we infer the limits at infinity from that. If we're doing it analytically, we go in reverse. We compute the limits at infinity and infer the horizontal asymptotes from those. And we do that within models.
Yeah, I want to know how to do it.
So let's talk now. Are there any questions on this graph before I talk about analytic methods? Cool. Well, let's talk calculator methods before we do analytic. Suppose I have some really nasty something like limit as x goes to 1 e to the x minus 2 all over x minus 1. And I ask you to evaluate this, and I ask you to evaluate this in a setting in which the calculator is available to you. What can I do on the calculator? I can do the 4 things with the calculator. I can evaluate functions. I can visualize. And I can find derivatives or differentiate. And the 4th thing you don't need to worry about yet, I can integrate. But don't worry about that just yet. So here I have something, and I check my form. Oh, this needs to be actually slightly different so that my form works out here. So how about there? That works. Now I check my form here, and I have e to the 0 minus 1 minus 2. Let's make that plus 1 there, so that my form works out to 0 over 0, and we have a legitimate problem. So my form is 0 over 0, and that tells me that there is a common factor here. However, I can't see a common factor. In fact, I don't know how to factor e to the x minus 1, blah, blah, blah. But I have the calculator available to me, so I'm going to evaluate this limit on calculator. How? We're going to let y1 equal the whole thing. Grab your calculator and do that. Please do not forget your parentheses, because the horizontal fraction bar is a grouping symbol. And the slash is not. So we let y equal, let's see here, parentheses, e to the x minus 1 plus x minus 2 Divided by x minus 1. There we go. That looks good. And now we're going to set a window size. I'm looking for the limit as x goes to 1, so I'm going to set a window size that fits that. How about x is between negative 2 and 2? That should work. Yes?
For the top part of the fraction, is it usually x minus x?
It's plus x. Yeah. Should be plus x. And I graph this fellow right here. When I graph it, I get a nice little graph right there. You can just barely see on your graph maybe that there's a hole in the graph right at x equals 1. And we aren't surprised at that because we know that at x equals 1, then the function does not exist because it would require dividing by 0. So how do I evaluate the limit? I can't evaluate it by plugging in x equals 1. If I do, the calculator will very sensibly tell me that there is no y value. So instead, I appeal to my definition. What is f of x arbitrarily close to when x is close to but not equal to 1? Give me a value of x that is close to but not equal to 1. 1.0001. So I hit trace. Yeah, there we go again. I hit trace. There we go. And I plug in x equals 1.0001. And I get a y value of 2.00005. Well, that looks pretty promising. And now I have to check the other side. This gives me the limit on the right. From the other side, give me a value of x that is close to 1 but a little bit less than 0.9999. And I get 1.999995. Based on this evidence, what is my best estimate for the limit? 2. It's exactly right. If you're working on a calculator question, what kind of work would you need to show? You don't need to show any of this. All that you need to show is the answer. Yes, I plugged in the function here.
Please,
Oh, okay, I wrote it down.
Okay. Yeah, I ended up modifying the function because it wasn't quite what I thought it was when I wrote it down the first time. So really check and make sure you got the function.
Mr. King,
Yes.
do you think it was
Probably it's a grouping symbol issue. See how you got that vertical asymptote right there? That almost guarantees that you didn't group it
I
correctly.
put it in the same as my part.
Yeah, you have x plus 1 instead of x minus 1. Yep. Now you graph it. Good. See?
Ah, thank you.
Yep. Other questions? Good. So calculator methods, enter the function, check x is close to your target value, and you're good to go. Yes?
Like on the midterm, can we just do that? And then
Yes.
are there going to be like directions where it's like you cannot use your calculator? Like you must do the analytics.
Only on non-calculator section. It'll be really obvious. Yeah. Now, what analytic methods do we have? We're computing the limit as x goes to c of f of x. Okay. Limit properties are a huge deal. We need to be able to leverage our limit properties. It's easy to remember them as slogans. The limit of a sum is the sum of limits. The limit of of a difference, difference of limits. Limit of a quotient, quotient of limits, unless the denominator goes to 0. That's right. The limit properties are useful in a wide variety of circumstances. And in particular, if you happen to know that your function is continuous, then you can evaluate the limit by direct substitution. Why can I do that? Because if my function is continuous, then by definition, the limit as x goes to c of f of x is equal to f of c. I can simply plug in. So that allows me to take a look at some complicated something like the limit as x goes to pi over 2 of x sine x minus cosine x. And I look at this and I say, sine and cosine and x are all continuous functions, and the difference of the continuous function is also continuous. I don't need to monkey around here. I can simply plug in, and the sine of pi over 2 is 1, the cosine of pi over 2 is 0, and I'm done. So direct substitution for continuous functions is the way to go. The problem comes when my function is not continuous, when I have especially a form of 0 over 0. This is the indeterminate form, and it indicates that there is some sort of common factor to be canceled. And in that case, I can use the alias theorem together with my techniques of cancellation and rationalization to evaluate the limits there.
Sorry, can you scroll down?
Sure. If, on the other hand, my form is something else over 0, k over 0, where k is not 0, then this is the infinite form. And my limit is going to be either plus infinity or minus infinity, and the only question is which one. And in order to determine that, I need to do some sign analysis to determine if the top is positive or negative, and the bottom to determine if the bottom is positive or negative. Most of you are good at actually analyzing, but we need to work, some of you need to work on how you write your results. So let's take a moment to do that. Let's consider one of our famous functions, f of x equals 1 over x. And we wish now to evaluate the limit as x goes to the left of 1 over x. This is our problem. It's posed to us. And here I want you to watch how the work is shown, because I have some of you that are doing dorky things with it that we don't want to do. The first thing is that I'm going to check the form, and I'm going to announce that by saying form. And I check the form simply by doing direct substitution. And there it is, the form is 1 over 0. I will not say that this limit equals 1 over 0. That's the kiss of death. That means immediately you're wrong. Because nothing is ever equal to something divided by 0. That's not a number to be equal to anything. You can't divide by 0. Now for the sign analysis. The sign analysis is also going to take place over here. And I consider the signs of the top and the bottom. The sign of the top is obviously positive. 1 is a positive number. The sign of the bottom is going to be done by carefully plugging in numbers that are close to but less than 0 in my mind. Mental evaluation here. I think about a number that is close to but less than 0. It will be negative. And therefore, when I plug that in, I get a negative value. This tells me that my limit is going to be positive infinity or negative infinity? Negative infinity, because I'm dividing positive numbers by negative numbers here. and I package my answer just like this. All of this is scrap work. It does not appear in your main equals stream. The other thing that does not happen is that I do not get evaluation of your limit by choosing numbers that are close to 0 and plugging them in here. So for example, I had some people that were trying to do this. And this is simply wrong. It's the wrong value. It's the wrong limit. Why is this wrong? Because I'm not asking what is the value of f when x is negative 0.001. I'm asking what is the limit as x gets close to but not equal to 0. This helps me to determine this, but it is not the actual limit itself. Does everybody see the difference on that? So none of this. Good? Questions? Okay, great. All right, so that's evaluating limits with sign analysis. Check the form. And this brings us to limits at infinity. The reason we evaluate limits at infinity is to find horizontal asymptotes. And so a typical question might be something like, find the horizontal asymptotes of f of x equals 3 minus x squared over 2x squared plus 1. Something like this. And so I begin by evaluating the limit as x goes to positive infinity and the limit as x goes to negative infinity of f of x. And now, in order to evaluate these limits, I'm going to use end models. Reasoning that as x gets really large, then 3 minus x squared is going to be basically negative x squared. And 2x squared plus 1 is going to be basically 2x squared. Take any really large number, multiply that by 2, and then add 1. The adding 1 contributes nothing to your value. And this allows me to immediately cancel common factors and get a limit of negative 1/2. Same process happens here. And there you go. For purely rational functions, one polynomial or another, these two limits will always be the same. For more exotic functions, like exponentials, or functions that are not rational functions, then those two limits will not be the same. Now, I've got my limits. How do I use them to actually package my answer? I'm going to package my answer like this. The horizontal asymptote is the line y equals negative 1/2. Please notice that the horizontal asymptote is not negative 1/2. It is the line y equals negative 1/2. Good? Okay. Where from here? Yes. We had 3 famous limits, or 3 special limits that are famous. And you can expect to see some variations of these. The limit as theta goes to 0 of sine theta over theta is 1. The limit as theta goes to 0 of 1 minus cosine theta over theta is 0. And the limit as theta goes to 0 of e to the theta, or let's do it as h. The limit as h goes to 0 of e to the h minus 1 over h is also 1. These three special limits were used to get the derivatives of sine and cosine and e to the x. And so tomorrow we'll address how we use them. What happens if I have some variation on this? For example, what happens if I have the limit as y goes to 0 of sine 3y over 2y, something like this? Well, I can evaluate this by doing a little bit of substitution and also limit properties. I notice here that the 2 is a constant that can come out. And I notice that I have 3y as the argument for sine, but I have y in the denominator. And so I'm going to fix that problem by doing a little bit of substituting. I'm going to let w equal 3y, or I could let x equal 3y, either way. And if w is 3y, then y is w over 3. And so I can now replace everything in sight in terms of w. The 1/2 is what it is. As y goes to 0, check that. What does w go to? As y goes to 0, direct substitution, what does w go to? 0. We have sine of w, and we have y, which is w over 3. And what we've done now is to transform the entire limit from one variable into the terms of another. And here's how this helps us. Because division is multiplying by the reciprocal, so that this is the same as sine of w over w times 3 over 1. What is y equal to? W over 3.
So where's the 1/2 for this?
The 1/2 was a constant multiple to begin with, and so I used the constant multiple rule for limits to pull it to the outside.
The last one you write down. No, not here.
Oh, why didn't I just pull that out like so?
Why do you write 1/3 instead of 1/2 and then you limit? It's W for
Oh, because I had 1/3 on the brain. Thank you. That's right. Thank you. Very good. Good catch.
I'm so confused now. How do you get 1/3?
No, that was just me being dumb. And now the 3 over 1 comes to the outside. And this is finally in the form of my famous limit, and it has a value of 1. So that I get 3/2 as the final answer. Right, so I hear a little bit of consternation on this one. This substitution process you want to walk through carefully so that you can see how it goes. We will be doing a lot of substituting in the second semester when we get to Andrews.
Hey, Mr. Taylor.
Yes, sir.
Never mind.
Okay.
No, never mind.
Okay. The last thing that we did with our limits was to consider continuity and discontinuity. We said that f of x is continuous at x equals c if the limit as x goes to c of f of x is equal to f of c. And one of the things that I had you do was to check functions for continuity. If this is somehow not true, then my function is discontinuous at x equals c. And we use the limit to classify our types of discontinuities. And there were 3 types of discontinuities that we considered. What were they? Jump was one. Asymptotic is one. And removable was the third. That's exactly right. And each one of these has a specific definition. And if you know the specific definition, it will make it easy for you to classify. Removable discontinuity. My limit as x goes to c of f of x exists, or I should say is equal to some value L, but it is not equal to f of c. Why is that important? The fact that the limit exists means that my graph has a nice little hole in it, right? But the fact that it's a hole and not a filled-in dot means that that limit is not equal to f of c. If it did equal f of c, my function would be continuous at that point. Jump. The limit as x goes to c from the left is a different value from the limit as x goes to c from the right. And asymptotic, the limit as x goes to c of f is infinite, either plus or minus. There are three famous and easy functions to illustrate each one of these. For the removable discontinuity, my favorite function is sine x over x. You can see from the form is 0 over 0. The function does not exist at 0, but the limit as x goes to 0 is well known. What is that limit? 1, because the limit exists but does not equal the function at that point, removable discontinuity. And the graph looks just like this. Here's my goal. Jump discontinuity. The famous function to illustrate this is x over the absolute value of x. The limit as x goes to 0 from the left, negative 1. So limit as x goes to 0 from the right, positive 1. Therefore, my function must jump immediately at x equals 0. And the classic famous function for this one is 1 over x. As x goes to 0 from the left, negative infinity. As x goes to 0 from the right, positive infinity. Because I have infinite limits, I therefore have a vertical asymptote in the graph. Asymptotic. That's plenty good for today. It's kind of amazing that we just did all of October in one day. There it is. It seems a lot less weird though than it did the first time around. Yeah. So make sure you practice.